will start the second presentation. This will be delivered by Mike Turquette and named "So you want to write a Linux driver subsystem?" ? Please go ahead.
All right, thanks everybody. Is the volume okay for everyone at the back? It's okay? Yeah. All right, so my name's Mike Turquette. The purpose of this talk is to discuss designing a Linux driver subsystem from scratch. If you're in the wrong place, too bad, the door's closed, you're trapped. Okay, so who am I? Why am I here? I'm the CEO of BayLibre. BayLibre is a small embedded Linux consultancy. Benoit here in the front row is the CTO. He's also attending the conference. He'll give a talk tomorrow. Previously, I was at Texas Instruments, Linaro, a spectacularly failed San Francisco startup, which was a lot of fun. I've contributed over time to a lot of different power management frameworks in the Linux kernel, CPU Freak, the clock framework, obviously, and then some other areas as well. I currently co-maintain the clock framework with Stephen Boyd. That was merged in 3.4, and you'll hear a lot about the clock framework today, maybe too much. It's the piece of code I'm most familiar with, and so I use it in all of my examples in this talk. There were a lot of mistakes made while writing that. You're going to learn from those mistakes. And also, this talk itself is an ongoing process. This is the third time I've given it. It changes every time. If you have any feedback, any comments, if you think it sucks, just let me know. Just tell me. It's very useful. So, oh, is it working? Okay. So one important thing to say at the beginning is that these are mostly my opinions. These aren't facts. Framework design is a matter of taste. There's a lot of opinion that goes into it. Different people on the mailing list will have different opinions, and that's okay. It's just that my opinions are right. And so, but no, feel free to disagree with them or to ask questions or to challenge them. In fact, throughout the slides, just raise your hand and just interrupt me at any time if you have a question or if you have a disagreement. I mean, I would prefer for it to be interactive if possible. So let's start about with our agenda here. Basically there's 4 parts to this presentation. At first, we're going to see what makes a good subsystem, sort of define what a subsystem is in the Linux kernel, design considerations, good patterns or pitfalls and problems you want to avoid. I will give a very brief overview at the end about the Common Clock Framework and where it fits in the design patterns that we'll discuss today. And then finally, I'll talk a little bit about maintenance and maintaining your framework after it's been merged into the kernel, which is a very, very important part of it. So the first section here, what makes a good subsystem. So let's start by defining some terminology, and these are my own terms. I just made them up. So we have a subsystem is really a framework or a library. It's a piece of code that implements a common behavior or a protocol or an interface, which is common and used across a lot of different hardware. Examples of that would be like the MMC subsystem, right? I mean, MMC is a standard, but the hardware for it is different. I use the word providers to describe Linux kernel drivers that they plug into the subsystem and they provide access to the hardware. I use the word consumer to describe other Linux kernel drivers which are consuming this stuff. They're getting resources and they're making use of the framework. They're the users of the framework. And interestingly enough, a Linux driver can be both a provider and a consumer when you use this terminology, and we'll discuss that a little bit more later on. Again, these definitions are my own. They're not baked into documentation or anything like that. Maybe someday we'll make them official, but not yet. I also use, I'll use the words framework, library, and subsystem in today's talk, and those are all kind of the same thing. I use them interchangeably. But to be specific, I use the word framework to talk about some kind of driver subsystem that creates a struct device, if you guys are familiar with the device model. And I use the word library when you're doing the same thing, except you're not creating a struct device. It's a library is just some reusable code where it doesn't create a struct device for you. It just does some operations which are common and reused. And you'll see more about that as we go. So, okay, here's a few examples of some existing driver subsystems, which some of you may have worked with before. So if you've ever worked with any of these, written a driver for them, then you've used Linux driver subsystems. There's a bunch of other stuff I'm leaving out here. I didn't put TTY or networking or block IO or any of that. These are just the ones that I use mostly, since I work on a lot of ARM embedded systems. So what makes a good subsystem, right? It needs to solve for the most common case using the Pareto principle. Right, about 20% of the effort will solve for about 80% of the use cases. You don't have to over-engineer it from the start. Just basically find out ask around, talk to the other developers. What are the core requirements that everyone has in common? And you want to solve those basic problems first. Don't try to solve every issue at the beginning. A subsystem needs to be maintainable. That means a lot of different things, but the code needs to be clean, it needs to be good quality, it needs to be reviewable, and it needs to be refactorable as well. Concurrency and locking are super important. You need to get that right from the beginning. We live in a world with SMP, we live in a world with preemption, and so this is a very important topic. It needs to respect the driver model, and I'll get into details about what that means later on. But the Linux driver model is a real thing, and you need to play nicely with it. A subsystem needs to be architecture and platform independent, and this can actually be sort of hard to get right at first, because most of the time when you're writing a new piece of code, you have your platform on your desk, your board on your desk that you're working with, and you just solve the problem for that board. But you have to think more broadly than that. You have to make it work for different architectures and different platforms within an architecture. Needs to be module safe, need to be able to unload and reload your modules and things not fall over. And also continuous testing, which I'll go into a little bit of detail about. Good ways to do that, and some existing resources out there that'll help you test. Another point is that if you write a new subsystem or a new driver framework, it's a toy until, it's basically a little toy until you have at least 3 users of it that are actually hammering on the thing and finding all the weaknesses. And once you start to have 3 or more users, then it'll become more of a mature and robust piece of code. And what you really want is to get people that are writing drivers for different chips from different manufacturers that have totally different types of hardware to use the subsystem. That's when it'll get very robust and very mature. So one thing you can do is bribe people with beers at conferences and things like that to sort of get them to adopt your framework as quickly as possible. Obviously, you want to write good code, right? And so, you want to use good programming practices. Basically, writing pretty code or non-ugly code will solve like almost all of your problems. You have to be very focused on consolidation. So when you're in the process of reviewing patches on the mailing list, if you see a lot of drivers that are open coding the same solutions, they're kind of doing the same hack over and over, write a helper function for that. Put it into the core of the framework and expose it via a header so people can use it and they don't have to re-implement the same stuff over and over. On the flip side of that, don't over-engineer, don't provide helpers if no one's using them, don't expose data structures that no one is actually actively using or asking to use. Every little helper function that you have internally doesn't have to be exposed via a header either. So there's sort of a balance there. Use Coccinelle. Coccinelle has a very high learning curve, but it's worth it to spend time learning how to use that tool and how to actually write the semantic patches so you can find problems and fix them. And then if you're not up on your algorithms and data structures, I recommend just taking the time to read a book. I think that Steve Skina's book, the Algorithm Design Manual, is quite good, and getting the right data structures baked into your code from the beginning is super important. Okay, so the second part is really the actual design recommendation. So everything before now was kind of fluff. Now we'll get into a little bit more detail. So this is the agenda for the talk. Before we get into it, are there any questions so far? Like, are people like, what's a Linux device driver subsystem? Nothing like that? So, what's Linux? Okay. How do computers work? So, okay. All right, so before we get into the actual recommendations, I think it's very helpful to look at Rusty Russell has these API levels, and there's a couple of links off to the side. You can get the slides later on and look at those. And these are 2 blog articles he wrote, which are actually really funny. He created this list of API levels in terms of quality, and then one of the other lists is how to write an API that people will hate and that you will, you'll make enemies if you do that API. And it's kind of a funny read, but it's actually useful. So at the bottom of the list here, this is bad, and at the top of the list, it's good, right? And I've circled here number 2 and number 4 because actually the clock framework is, I would say most of it is number 4, which is that if you follow the common convention, when if a guy's going to come in here and write a clock driver, as long as he basically copy pastes the code that other people have written, then he'll be okay. Like the driver will work fine. And there's actually nothing wrong with that because let's face it, when you write a driver, the first thing you do is you copy and paste like someone else's driver that was recently written. Like that's how we all start to write a driver. Very few people like open up a text editor and they're like Vim or Emacs, totally blank. I'm just going to write this from scratch, you know. I have the GPL license header memorized and I'll never have to copy that. Like, I mean, no one does that. So it's okay if number 4 is as good as it gets. Unfortunately, there's a couple of tricky spots in the clock framework that I would say are level 2, where if you really, like actually rounding rates for clocks is very tricky. I mean, you know, do you do floors? Do you do ceilings? Are you trying to get the exact rate? And you basically need to read the implementation in the core code to understand how it works. So, you know, just an honest evaluation of my own API there. So keeping this in mind as we go further, let's talk about the details of like how to craft a framework and what are the design stuff you have to think of at the very beginning. Probably the most important like high level topic is the split between the consumer side of the API and the provider side of the API. And so you know, consumers, they want to get devices and resources and call some function on them. So usually these are get type functions that you see. Clock get, maybe you want to do clock enable the clocks, you want to, you know, set the rates. These are things that consumer devices are going to do. Like, you know, a video IP block might need to get the clocks that power it. The driver for that will get the clocks that power it, and it'll decode some video, and then when it's done, it can, you know, disable the clocks and put them. On the other side, you have the provider, and in the clock framework, this is the clock provider driver. This is a driver that maps onto a piece of hardware that actually generates clock signals and provides them to all the downstream IP blocks. And really, these APIs should not mix. It's very easy to just write one big header that has like everything in it, and you want your consumers and your providers to include that header and use it, and that will totally be a bad idea later on. Like, you'll regret doing that. You should split it at the beginning, think long and hard about what the differences are between these APIs. And an important question to ask yourself is it ever valid for the consumer and provider side of the APIs to mix? And for some subsystems, the answer is no. For some, like the clock framework, the answer is yes, actually. And there's some interesting examples of that. One kind of tip I have here is for the clock framework, we have the provider side of the API is in clockprovider.h, and the consumer side is in clock.h. And one of the things that Steven and I do when we're reviewing patches is we grep to see if both of these are ever included at the same time in a C file. And if they are, the first question we ask the author of the patch is why? Why are you doing that? Justify that decision to us. And we often find that people just aren't paying attention, and they just include every header known to man just because they're lazy and they don't want to figure out which headers to use. So as you end up maintaining code more and more, you should start to challenge that kind of patch. So here's an example of when this is just how hardware is made. It's just some blocks. This is an example of a real piece of hardware, and this is an example of when the hardware and the Linux device driver for it needs to be both a provider and a consumer. So the big gray block here, that's a OMAP3 ISP. It's a piece of hardware for cameras. And it consumes a clock signal. It's called camera M clock, and that comes from I don't know some other dedicated piece of clock generated hardware, and it consumes that clock signal, and that's like a normal thing. Most IP blocks do that. But then within the camera IP block, you also have some clock signals that you generate itself. So this is an interesting example of a real driver. It's merged into mainline. It's been there for a long time, and it's both a provider and a consumer. And so can you mix these things safely? Can it be a clock consumer and get a clock and change the rates, but also provide its own clocks and not blow everything up? And so this is an example of why we actually had to solve this problem in the clock framework and make it safe to do that. The next point on the design tips is that you really should abstract away any hardware details in the consumer API. So basically, the consumer, the driver that's consuming whatever your API is, it should not have to know any of the details about the architecture or the platform that it's on. And in the following slide, I'll give you a good example of this. But what does that mean for the design of the framework? It means that the The dumber the framework, the more details that you're pushing down, you're adding to the burden of the consumer driver author. So if you have a really stupid framework that doesn't do a lot of smart stuff, then the driver authors that are consuming your API, it's gonna be a lot harder for them. They're gonna have to like manage a lot more details, and you'll solve a lot of stuff in open code. If you have a very, very smart subsystem, then you can only expose like a limited set of knobs to your consumer drivers, and we'll get into an example of that. For the clock framework, this means we do a ton of tree walks. I mean, like the graph traversal stuff is super complex. It's not at all easy for a new person to come in and read that code and understand what's going on, and that's okay. Because we want to make it easy for people to consume the API. If you actually want to hack on the core of it, then yeah, it will take some time to learn how it works. Another point, and this, I don't know if this will make sense, but another tip is that if the API that you expose to your consumer drivers is mostly write only, you cannot. That will help you a lot. If you make an API where consumers can query and see state from inside the framework, actually that will make your life a lot harder, because now they're going to start to bake in assumptions into their drivers about how things should be working. If you have a write only API, that helps a lot. So here's another awesome block diagram that shows an example of how we abstract away the details from consumer drivers. So again, we're using the MMC controller example, and it's consuming the clock signal coming out of this block here. Now in practice, in real life, this clock can be parented from either an oscillator or a PLL. This is how the hardware actually works. But for the MMC controller device driver in Linux, does it need to know that information? I mean, like, why is it important that it knows that maybe maybe this parent can clock this guy, or maybe this parent? It shouldn't have to at all. And so in the modern clock framework, we abstract that detail away. All you know is that you have this MMC clock signal coming in, and whether it changes the parents behind the scene, you don't care. You don't need to know any of that information. And that's a big improvement from the old legacy clock framework implementations, where every driver had to have a ton of if-defs and had to know a lot of details about the actual hardware underneath it. And so that should be a goal for any subsystem, which is that you present a very simple interface to your drivers, and you don't they don't have to bake in a lot of knowledge about all the different hardware that's out there. All right, so this is another interesting point. So devices versus resources. So the clock framework, it manages clock nodes as a resource, right? These you can have 300 clock nodes in a single system-on-chip processor. Do you really want each of those to be a struct device? Probably not. You're going to have your sysfs is going to explode and get really messy, and it's just it's probably not what you want. And so we decided to design the clock framework as what I call a library, where it manages clocks as a resource, but each one is not a struct device. You, as the driver author, are responsible for making a struct device. Typically, I think that doing platform drivers and getting devices out of that is like the right way to do it if you're making a clock controller driver. And this was a very conscientious decision from the very beginning. And it turned out to be a really good decision, because we see a lot of different types of drivers. I showed you the ISP camera driver earlier, but also reset controllers and all different types of drivers like to embed clock code inside. And it would be a big pain in the butt if each one of those was actually it created a struct device every time you registered a clock. So let's compare it to like the regulator framework. You guys, have some of you guys worked with the regulator framework before? Yeah? Okay. So the regulator framework, on the other hand, is very similar. Like regulators and clocks, you manage them somehow kind of similarly. But in the regulator framework, every time you create and register a regulator, you create a struct device. Now, in practice, that's okay, because on one system you may not have more than a dozen regulators, so it's not a big deal. But on a system where you have 300 clocks, it starts to become a problem. So this is just a decision that every subsystem designer will have to make for themselves at any given time. Should you do what I call a framework that creates a device, or a library that just manages resources? All right, so reference counting, everyone does reference counting, right? It's very important. When you have multiple kinds of consumers that are accessing the same resources, you need locking, right? And you probably need reference counting as well. And so in the Linux kernel for devices, we have two data structures which are important here. So K-object is, this is the default reference counting mechanism that comes inside a struct device. And if you look up the definition of struct device, you'll see K-object is already inside there. K-object's cool. It creates sysfs objects for you, like you get the hierarchy in the virtual file system, and you get all that stuff for free. So K-object's nice. If you're using struct device, you already have it. But in the clock framework I mentioned before, we don't create struct devices at any point when you register clocks or when you create a clock tree. Instead, you have to create your own. So we still want reference counting, though. So instead, we use kref. And kref is embedded inside a k-object, but it's also available for anyone to use. It's exposed in a public header. Anyone can use it. So we use kref in order to do our reference counting. And this is important to bring up just because a lot of people open code their own reference counting solutions. And the point is that the Linux kernel provides this stuff for you. You should just it's already there. It works really, really well. Just use it. You have options. Oh, and don't forget the release method for either of these things. So. Oh. Okay. All right, so I've been talking a lot about devices. I've been talking a lot about paying attention to the actual Linux driver model and device model. And here's an example of where it was the wrong code. This code doesn't exist anymore. It's been updated to do the right thing now, but several kernel releases ago this was around. And what's the problem with this code? Well, it's an init call. Actually, I guess the init call's not here. It's on the bottom of the slide. But this is just some spaghetti code. It had an init call associated with it. There was no actual driver, no actual device associated. This got called once when the machine booted up, and there was no accounting for which driver owns this piece of code. All we do is we just register some clock. And the right thing to do here is to create a platform driver instead. And actually, at like a late init call time, when platform drivers are actually registered and probed, that's the right time to register your clock. So this is kind of a nasty, ancient piece of code that I'm glad it's gone. So, but this was also a really, really common mistake that I saw early on before I created some helpers that made it a lot easier to do the right thing. Okay. Is it? Oh, it's animated. Great. So we're about halfway through the material, and I've done this talk twice already, and I know it's a little hard to just sit there and just absorb everything. So we'll take a moment here. Does anyone have any questions or any feedback before we continue into all the nice technical details? So.
Any questions or feedback? And still awake? Okay. Looks that
the sleeping people never respond when you ask that question. It's
okay.
Yeah. We'll solve that problem someday. So.
Okay.
Okay, fine. Then we'll just keep going. All right. So we're still in the design tip. This is the kind of a section of the presentation. There's just random design tips. There's no priority to them. They're just ones that I think are super important, and that sometimes they're missed. So locking and concurrent access is super important, and this is so true. Driver authors will just ruin your day. I mean, they will just, I'm sure when they wrote the code, they thought it made sense and it was a good idea, and they just did everything wrong. And when you're the subsystem author, or the subsystem maintainer, you realize how nuts the driver authors of the world are out there. Like you finally get exposed to the crazy train. And so, in particular, this happens a lot around locking. Locking is a thing that I guess it's easy to screw up. And you need to protect yourself and you need to protect your subsystem when it comes to locking. So how do you actually do that? What does that mean? All data structure access has to be wrapped around locking, and we all know that, right? Locks are meant for protecting access to shared data structures. But also, you have to be careful about the locks that you create. You should never expose your lock structures to drivers in a header. Like, don't put your struct spinlock or your struct mutex in a header. And I know this does happen a lot in the Linux kernel, and sometimes there's good cause to do it. But don't design it that way just from the beginning. Only do that when you decide that you really need to share those locks somehow. Also, don't even declare the locks in a public header. Instead, what you want to do is, or if you have wrapper functions like if you have a function called lock my awesome framework and then another function called unlock my awesome framework, right? Don't even expose those in a header, right? You can use those internally inside of your, the core framework code, but don't expose those functions at all to for drivers, because they'll, a driver will have one thread over here that, locks a framework, another thread over here that locks a framework, and they'll both depend on each other, and now you've deadlocked. And there was no good reason to expose that to the drivers at all, right? So what's the right way? I've told you what not to do. The right thing is, at your top level API that you expose in a header, that will always take the locks internally and then release the locks, and then it will return. And that sounds very simple. But the point is that, the actual locking resources should never be exposed to drivers. They will just deadlock the whole machine and mess everything up. And so you're really in charge of, creating an API that handles all of the locking bits completely internally. And if drivers need extra synchronization, then they must create their own locks, and that's okay. Like they need, you shouldn't try to help them out by letting them borrow your locking scheme that you've created in your subsystem. Let them sort their own synchronization problems out separately. All right, so here's sort of an interesting real-life problem that we had. So the clock API is actually quite old. I mean, it's been around for years. It predates the common clock implementation. And I inherited that API, and so it brought some baggage along with it that I had to deal with. One piece of baggage, which was not very fun, is this whole idea that clock enable is a function and clock disable. There are functions you can call in an interrupt context, which means, they have to be fast and they cannot sleep. But there's a lot of hardware out there. Let's say you want to enable a clock, and it actually requires I2C message to do that, because you're going out over the bus to talk to some other expander chip or something. And so, or you're talking to a PMIC, and the way you communicate to it is over I2C. In this case, I2C can sleep, right? I mean, the framework uses a mutex. The operation itself can be pretty slow. So a while back, there was a clock prepare was created. And so you have clock prepare, which is basically for turning on slow clocks, clock enable, which is for turning on fast clocks. And now you have two different kinds of locks, because one is protected by a mutex, one is protected by a spin lock. I mean, this is a recipe for disaster, right? Because you're accessing the same bookkeeping data structures inside the subsystem. It's all the same code, but different locks. So how do you design an API where you won't have problems with this? And actually, the solution isn't really technical at all. It's not that we devise some like really smart way to detect which lock is held and do the right thing. No, instead you just make rules, and if someone breaks them and their system locks up, it's their fault for breaking it. And the rule is that you always call clock prepare first, and not only do you call it first, you wait for it to complete. It must complete. And then when it completes and returns, then you can call clock enable. And you must always go in that order. You can never flip the order around. And as long as you always keep that order, call clock prepare, then clock enable. Later on, you can call clock disable and then clock unprepare. As long as you keep the same sequencing, lock dep won't give you any warnings, and you won't ever lock the system up. So these are the sort of like weird stuff that you might encounter if you're inheriting a legacy API like this. Here's another nice diagram. These are really good diagrams. And this was a really bad day for me, because some patches were merged, well, I was asking a bunch of people to convert their platforms over to use the common clock framework, and in the process we exposed a massive bug where like all of the I2C subsystems stopped working, and that was not a very fun time. And so let me just try to explain what's going on here. So food device, it has a driver, and it calls clock prepare on this I2C clock. And the I2C clock is actually on a PMIC, right, or a clock controller or expander. And to enable it, it has to use I2C also to send it goes into the I2C subsystem, and the I2C subsystem also calls clock prepare and clock enable. So you got this thing, it's calling clock prepare, clock enable. It goes into the I2C subsystem, which also calls clock prepare, clock enable, all in the same context. Deadlock, right? You've totally broken all I2C transactions now. And so this was a really bad problem, and me and a couple of people scratched our heads over it. It never came up before the common clock framework existed, because everyone had private definitions of struct clock, and we just got away with it just by chance. This problem was just kind of avoided silently for years. But now that we have a single implementation of struct clock, we had to solve this problem. And so how did we do it? we created a reentrant locking scheme. And actually, several people have copied this and used it elsewhere in the kernel, and I don't know if this needs to be generic, or actually maybe someone in the audience will spot a bug and say, oh man, I can't believe you're doing that. That's super unsafe. But I don't like code in presentations, so I'll just blow through this really fast. But the point is that if you're, if you're thread A and you hold the lock, and then later on the same thread A tries to hold the lock again, we'll detect that and just keep on going. So you can re-enter the framework as long as you're in the same thread context. If you're thread B and you come along and try to hold the lock, you're like, oh, thread A's already got it. I'll just busy wait, right? So it's a pretty sensible, kind of obvious solution. Hopefully it doesn't like introduce a giant security hole in the kernel in like 5 years or something. So. All right, so I mentioned this earlier. You got to protect your data structures and bookkeeping, and I talked a little bit about doing that with locks, not exposing certain things into the headers. But that expands to like a lot of different stuff. It's not just about protecting the locking structures and helper functions that you create, but really all the bookkeeping, all the data structures that you create, which are really internal. Like if you have some reference counting or you have some like private data that doesn't, that's totally internal to the framework, you should never expose that to drivers. And there's a couple different tools to do that. So opaque handles is one of the most obvious and best tools that we've had for years and years and years and years, ever since C was created. So what that means is you can declare a structure without defining it in a shared header, and people can have different drivers can have a handle to that structure, but they'll never be able to dereference it, right? And so that's really one of the best things that you can do early on while designing your subsystem is if you have an internal bookkeeping structure and you want drivers to know that thing exists, but you don't want them to dereference it, only declare it. Don't define it in a public header. There's a lot of bits of code in the Linux kernel where the author just sort of naively defined the whole structure in a public header and lived to regret it. And even Greg Kroll-Hartman told me that he really regrets that some of the struct device and sysfs stuff is all publicly defined. I mean, because there's bits of bookkeeping that anyone can just reach in there and touch it and change some pointers and muck around with it. And so this is coding defensively, right? You want to code defensively and not share anything that you don't have to. If you are going to give provider drivers access, think long and hard about how to do it. For those of you that are familiar with object-oriented programming, probably accessor functions are the safest thing to do here instead of actually not actually defining the struct itself. And then if you're going to provide access to these resources, you're going to want to use get and put type semantics around that, so you can keep track of how many people are accessing it once. That way, if you do a module unload or some other operation where you unregister a resource, it doesn't just disappear while someone's trying to touch that memory. The bottom line is that for internal bookkeeping inside of a framework or a subsystem, you should just count on drivers screwing it up and doing the wrong thing, and you have to code very, very defensively about that. All right, so again, more code on slides, sorry. So on the right side, we have struct clock core. This is a private internal bookkeeping structure inside of the clock framework. And no one has any business at all knowing what's inside of here. None of the drivers have any business knowing the details of this structure. In blue, we have a couple of reference counting mechanisms, which are cool. And what this is used to illustrate is this idea of per user reference counting. So it used to be that like the left side of this screen didn't exist. This was the only thing, and we would just count references within the framework of how many people are touching this resource. But after a while, we had some patch sets come in that introduced per user reference counting, and this is really cool. The structure we have both structures. They look very similar, but this gets allocated on a per user basis. So every single time a driver calls clock get, we actually allocate a new one of these struct clocks, and we keep a separate prepare count and enable count on a per user basis. Why is this important? If you have, let's say, reference counting mismatch, let's say someone calls get once, and then somewhere else in the kernel put gets called twice, right? That's a mismatch, right? It's not symmetrical. And so we were always able to detect that with just the right side of the screen. We were always able to say, oh, the reference counting's wrong, but we couldn't tell you where the bug in the code was. Now with per user reference counting, you can say, I'm only counting references that come from this specific user in this data structure. So if there's a mismatch, you know exactly which driver caused it. This is a small thing, but it really aids debuggability, and it's a good design practice, you know, when you're thinking about how to design your subsystem from the very beginning. All right, so this is another Getput bug. Again, Getput accessor functions are just like a fundamentally good idea, right? In this one, you know, we have a probe function. It gets some stuff, it does some stuff, and then it releases the resource, right? And then in the module exit, we do something again with that resource that we put. This seems like a very obvious bug that, you know, it's super obvious and it should never happen. I lost count of the number of patches I've reviewed that have this kind of bug in it. And now we have Coccinelle and other cool tools that will sort of try to catch these bugs automatically. But this is exactly the kind of thing where if you can have some defensive programming around this, maybe you can catch it very early on. Even if you don't catch it in review, you know, maybe you have some smart warns or some bug-ons or something like that. And I mean, again, it's like an obvious piece of bad code, but it happens all the time. All right, we're almost through with the design tips part. How are we doing on time? Okay. So one of the last things I want to talk about is if you're designing the API from scratch, whether you should have a synchronous or asynchronous API. And so, you know, synchronous is sort of the obvious thing to do. Whenever anyone writes some code the first time, by default, you sort of write like a nice, you know, synchronous interface. Execution is blocked until the operation completes. And it's really sometimes the only right choice for certain low-level types of operations where asynchronous behavior doesn't make any sense at all. Async, on the other hand, you know, you can basically return to the main thread immediately and then get notified later on when the work is done. There's some performance benefits to that in certain cases. In a lot of cases, there's performance benefits. And it requires a model where it makes sense. And since we're talking about device drivers, we're talking about interacting with hardware, this doesn't make sense for all hardware. So the two questions that I always ask when people say, oh, are you going to make an asynchronous version of the API is, well, does that make sense for the types of resources we're managing and the types of hardware that we're touching? And then the second one is it worth it? I mean, it takes some time to get that right, to do it the right way. What's the performance increase? Is it really buying you a lot? And is it maintainable? So who will use it, et cetera? Let's see, I think this is, yeah. So the other question is, you know, where does the data come from for your framework that you're creating? So, you know, in the dark old days, we used to have like board files, and we also had like platform data. But now there's a proliferation of different areas where data can come from. We have device tree in ARM and PowerPC and MIPS world. ACPI is evolving quite fast. ACPI used to be really CPU centric, but now they're adding like tons of data tables for all kinds of stuff that you see inside of a modern SoC. And one of the things that you need to do early on is try to create as many helper functions to get data out of these like firmware interfaces as early as possible. That way, the reason you need to do that is because like every single device driver that adopts your framework will have to open code those solutions if you don't do that. So it's best just to familiarize yourself with whatever the firmware interface is, even if you don't know much about it. Just, you know, dive in fully and learn how best what the best practices are and bake that knowledge directly into your framework. On the other hand, when you're designing a subsystem, let's say you're an ARM hacker and you're used to device tree, you should also make sure you don't design your subsystem only for the device tree use case, because you want other people to adopt it. You want other architectures to be able to use the code that you're writing. So it's this balancing act of like you want to quickly adopt all of these firmware interfaces and these places where all the driver data is coming from, but you also want to, you know, be able to scale your subsystem out for different types of architectures. All right, and then yeah, we're at the end of the tips section. So, you know, these are just some miscellaneous bits. Always do module testing. A lot of people forget to do this. You always find bugs that way. When you're designing your APIs, it's really easy to have like just like 2 or 3 arguments in a parameter list, and it ends up like growing to be a whole bunch of arguments over time. Save yourself the trouble and just pass in a pointer to a structure from the very beginning. That makes refactoring the code a lot easier in the future. when you're merging new drivers, as much as possible, enable in kconfig, enable a config compile test. This will increase test coverage a whole lot. And it works nicely in conjunction with kernelci.org, if you're familiar with that project, and also with like the 0-day build robot. I like to make files lexicographically or alphabetically, like every other release, and that's probably just because I'm have obsessive compulsive disorder. But it's kind of nice to have everything nicely sorted every now and then. It also reduces if everyone just adds their driver to the bottom of the line, the bottom of the file, you end up with like a ton more merge conflicts as well. So having it just sorted just introduces an amount of randomness in where people put the lines, and it makes the maintainer's life easier. And then this is like by far the silliest nitpick. I mean, you can just ignore this one if you want. But if you have to deal with a bunch of data tables and drivers, which is true for clocks, we have huge amounts of data for clocks that we register. Always terminate lists with a comma at the end, because then and this is like a very silly nitpick, right? But that way, when someone adds another line next time, that diff is only one extra line instead of 2 lines, right? And like I said, it's kind of silly, but hey, the point of this talk is to discuss tips. So yeah. All right, so let's do a very brief review of the Common Clock Framework design. This would be like one slide. It'll cover everything we've talked about so far. So the clock.h API is like really old. It predates the Common Clock Framework itself. There's multiple implementations that are still merged upstream for different architectures. Maybe someday we'll get them all converted, but the point is that we're constrained by the fact that we can't just change the API whenever we want, because it'll break all the other implementations. The reason we wanted the single implementation is so that we could combine a bunch of different ARM platforms into a single Z image, which we did probably 3 or 4 years ago in ARM 32-bit land, which was a big accomplishment. It consolidates code, bug fixes for the single implementation will benefit everybody. It's just a good thing. And at the same time, also historically speaking, the framework was written at the same time as some other developments. Linus Walege was writing pin control and GPIO and all the pinmux stuff, which is in a very similar space. And also ARM was adopting device tree at the exact same time in parallel to this framework being developed. So it was kind of a tumultuous time in ARM land. So, okay, here's Clock Framework design in one slide. It's a library. It doesn't create struct devices for you. You're expected to bring your own. I recommend to most people to use a platform driver model. One of the benefits of this is it makes it a lot easier to combine the clock framework with other stuff. We often see reset controllers, and clock drivers mixed together, and other types of multimedia devices. It's quite common. We do have a mixed use of mutex and spinlock, as we discussed earlier. The best way to get around the issues with that is to just define strict rules of how to use the API and enforce them. We have per user opaque handles. No one can dereference any of the inner details of the bookkeeping or the internal structures of the framework itself. We do per user reference counting on all the operations, which increases debuggability quite a bit. We have a well-defined consumer provider API. And one thing I didn't go into, but actually it used to not be that way. We used to have everything all mixed together. And so I'm speaking from experience when I say that that's a bad idea. So we have unique headers that do consumer and provider split. If you look at the regulator framework, I think they have 3 headers. They have a header for consumers, one for what I call the providers, the machine backend, and then they have a 3rd header, which is actually for exposing some of the framework core internals, which is a little weird. But the point is there's more than one way to do this. Internal data structures are completely hidden. They're not even the internal data structures aren't even defined in a local header. They're totally only in the .c files, right? So they're just in C code. We use big global locks. We don't use any kind of fine-grained locking yet. We may at some point adopt fine-grained locking in the future. That's super hard to get right. We don't have an asynchronous API. It doesn't make sense for this type of stuff. If a driver enables a clock, on the very next instruction, after you call clock enable, it may do something that would brick the machine if that clock line wasn't physically toggling in the hardware. So for us, asynchronous API doesn't make sense. And we share the API with competing implementations. Maybe someday we'll get rid of those competing implementations, but that's an extra constraint. All right, so we're all experts at subsystem framework design, right? We all know everything. You guys have written your framework. It just got merged upstream on the first revision of the patch series, of course. No rework required. By the way, Clock Framework took 11 spins on the mailing list, 11 versions. No, you're not done at all. This is just the beginning. I mean, the maintenance of the framework is a much bigger piece of the puzzle. And so it's the beginning of the process, really. It's not the end. If you have what I call a popular framework, which just means that you expect to have quite a few maybe existing drivers, things that are already merged upstream, and they're going to convert over to whatever your new implementation is. That's what I call the popular framework case, right? The code already exists and someone needs to port it over. You should set aside 50% of your time to manage that, which is way higher than what most people think. I think software developers might be the worst at sort of overestimating their capabilities and underestimating how much time projects will take. They're like, oh yeah, half a day a week, maybe most 1 day a week. No, I mean, you're going to get buried under a pile of patches. You should set aside 50% of your time, and I recommend that you make sure your employer is okay with this before you commit to it. Otherwise, you're just going to have a lot of angry people on the mailing list with a non-responsive maintainer. So, how do you alleviate this problem? Well, finding a co-maintainer, or actually a big trend that we've seen in past years has been maintainer teams. So the ARM SOC tree is a good example of that. Arne Bergman and Olaf Johansson are the two main maintainers for that, but if either of them takes a vacation, then they'll bring in Kevin Hillman or someone else. The point is it's a big extensive team for people that can do that job. And so that really helps lighten the workload and kind of distribute the workload. The worst case scenario is when you have a maintainer who's a single point of failure. If they get hit by a bus or go on a vacation or something, then none of the patches get merged, and that's a big problem. As far as picking co-maintainers, if you're not sure who to pick, if you don't have an instinct like, oh, this is the perfect engineer to help me out, then one of the things you can do is just look at who's been fixing bugs in the core code, who's been submitting patches and adding features to not the drivers, but the core framework core code itself, and just pick from the top contributors there. It's very important to pick someone who you can communicate well with, because you're going to be doing a lot of back channel stuff on IRC or private messaging. So make sure that you can communicate well with them. It helps to have similar types of humor and that kind of stuff as well, assuming you have humor. But if you don't, then don't worry about it. Participate in Linux Next. So the Linux Next tree is one of the greatest inventions of the Linux kernel development community. As soon as you have a public Git tree with patches in it and your stuff's been merged upstream initially, then ask Stephen Rothwell to add your tree to Linux Next. This will greatly increase code coverage and testing, and you won't get yelled at by Linus Torvalds near as much if you use this mechanism. You'll avoid a lot of problems. It also helps people to encourages review of the code, yeah, it's just a great idea in general. So. The other thing is that setting up a subsystem-specific mailing list or IRC channel can be a really good thing. I actually avoided doing that for a long time. I don't know why. I mean, it's really helpful. If you can separate your mailing list traffic out from like LKML, which is this giant fire hose, right? If you have one that's specific for your subsystem, that just helps you out. It just makes maintenance a lot easier. You know that any patch that goes to that mailing list is a patch that needs your attention. It just makes the process quite simple. The IRC channel stuff, if you like to use IRC, then set one up. I think IRC usage is sort of dying slowly, but it's there's still people that use it. It's still helpful. I guess everyone uses Slack nowadays. So, and then the other thing is try to automate your whole life. And I know everyone says like, oh, someday I'm going to take some time and automate this highly repeatable process. And it's really worth it. I mean, even if you take a few days. To just automate that whole maintenance process, or even if it takes you a week, it's well worth your time, because you'll just save so much time down the road. And ideally what you would like is, one thing that I have is that when I'm doing patch review in my mailer, I mean, I hit a single button and it will apply that patch to the right branch on my tree, and it will gather all the act bys and all the tested bys, and it'll add my signed off by to it. And it's just one button that does that. And you can look at my dot files on GitHub if you want to see how I implemented it for my particular email setup. But if you have any, I don't know if any of you guys have seen Greg Kroll-Hartman give his talk on how he does stable releases. But I mean, it's amazing. You want to talk about a guy who's really automated everything. I mean, just the entire process of reviewing patches and applying patches and then creating the release and pushing out Git tarballs and all of that. It's like super automated. I mean, if you can automate your coffee maker, you should. Like that will seriously improve your life. All right, and so we're almost near. This is the next to last slide here. So, some practical advice that I have is that, now that you're a maintainer, in a way, saying no is one of your primary responsibilities, and this is definitely part of the highly opinionated part of the talk, right? I mean, a lot of people disagree with this. Other maintainers I talk to say like, oh no, your job is to merge patches, but in a way, I mean, my personal philosophy is that quickly merging both good code and bad code into the kernel is more harmful than only slowly merging just good code, right? And that's my personal philosophy. It's okay if you disagree. You're just totally wrong if you do. But you know, that's just my philosophy. I also think that one thing I struggled with personally was that sometimes I'd look at a patch and I wouldn't have a really strong technical reason to not do it. Maybe I thought like someday we're going to implement a better way to do that, but I don't have time right now, and I always hated to tell people that kind of thing. Or maybe I just, you know, it was just somehow a disgusting, ugly patch, and I just hated it. I have a strong technical reason to knack it. And one thing I learned over time is that that's okay. Like you're the maintainer, you can just knack it. If you just think it's horrible, you know, just say that. And I really struggled with that for a long time, and I wish someone had told me, you know, oh, it's okay, Mike, you can just hate that patch and delete it. That will help your life actually a lot, you know, make things a lot better for you. If your instincts tell you that it's bad, then it definitely is bad. Especially if you wrote the code, you know more. You're more qualified than anyone else on the mailing list to really know what's good and bad for the subsystem. Wolfram's saying this was just at Linux Plumbers Conference, like just I guess 2 weeks ago or something in Santa Fe. Yeah, Wolfram gave a really good talk. This is a YouTube link where basically he just tries to explain like the mentality of a like a shitty maintainer who won't merge your patch, you know, and he tries to explain like his philosophy for the I2C subsystem and why he does things the way he does. It's worth a watch. And then another thing that took me by surprise is that at some point you may stop being the top contributor to the piece of code that you wrote. You know, if you look at git blame, you know, 4 years on, I mean, how many lines have my name next to them, you know, compared to other people's name? And you just have to get comfortable with that. I mean, other people have like really big feature requests or feature ideas that they want to implement. Big refactors of code may happen, optimizations, cleanups. You have to be comfortable. You know, you brought the code into this world, but at some point you kind of need to let it grow up and become an adult. And so that's okay. And in fact, if someone else is doing a lot of really good work, bring them in as a co-maintainer. Add them to the maintainer team, right? All right. Yeah. So I'm just going to let this loop in the background during the whole Q&A session. So please, if you have some questions, go for it.
Excellent. Thank you very much. So we have a question. Okay.
Hi again.
Hello.
I wait to the end of the presentation because I have more global question. One remark before about this practical advice and saying no. It's not always the case, but it's out of scope of this presentation, so we could discuss it later.
Sure.
So the question is, like you said about clock framework history, it was kinda ARM-oriented at the time because Intel has no clock framework, no clock tree, not at all about that. Everything was hidden in hardware. Nowadays, Intel comes with some clock implementations within IP blocks.
Right.
So the problem here is inside drivers, we have to implement producer and consumer simultaneously. So the first question, will clock framework to consider this and address this problem? And I will ask next question because it's logical continuation of previous one. Why not to hide clock framework to PM runtime? Because it's quite obvious that PM runtime should do the thing. Thank you.
Sure. Both are good questions. So Intel does have the LPSS driver, which was, I think, the first driver from them. Did you write that? Oh, okay, cool. Yeah, yeah. So you know that like has like 2 clocks in it or something, right? And actually, 2 weeks ago in Linux Plumbers Conference, I sat down with Raphael to discuss this problem, and it's a more general issue of basically ACPI wants to start to define clocks as power resources, and we discussed ways to do that. So I would say that it's sort of in progress. There's a bunch of examples that are merged upstream where you have a driver which is a clock provider, and it's also the only consumer of those clocks, right? We have this display subsystems for doing video out where they have their own PLL that drives the display, and they're the only consumer of that PLL. So I would say that pattern you're looking for, it exists already. It's perfectly acceptable. You know, it's yeah, just go for it. I can point you to some existing upstream code if you want to take a look at it. I completely forgot what the second question was.
About consolidation, clock framework, and
Well, yeah. So Geert wrote the PM clocks implementation, which is like a simple. If you're familiar with generic power domains, GenPD, which often goes together with runtime PM, these are all nicely developed subsystems, Linux driver subsystems, right? The PM clocks implementation does exactly what you're talking about. It implements generic power domains that only do clock enable and clock disable. And so for like simple systems that don't do voltage scaling or have power areas or power islands and things like that, if all you want to do is cut clocks, then actually there is an implementation that works for that. So the Renaissance guys wrote that for their chips, and it's available today. I think that clocks aren't only necessarily a power issue. If you're working on audio drivers, for instance, and you have to support 44.1 kilohertz to get your MP3 playback stuff working, that's not a power management issue, right? You have like a multimedia use case that you have to configure for. So I don't think we ever want to hide the clock framework from drivers. It's a perfectly reasonable sort of framework for drivers to use to achieve use cases besides just power management. So I don't think we'll ever hide it completely into runtime PM or GenPD. So.
Okay, so thank you. Next question.
Thanks for your talk.
Yes. Thank you.
When you started to work to try to merge your subsystem, did you already have some authority in the kernel community? Did you feel some back pressure, and how did it come?
That's a great question. Yeah. So, yeah, I was definitely pooping my pants the whole time. I mean, it was a very nervous kind of thing for me to do. I had some reputation within the community, but actually, if you look at my patch count before the clock framework, if you look at the Git log, I mean, I have very few patches before implementing the framework that were merged upstream. I had participated in a lot of discussions online because I was familiar with power management, and I was really familiar with sort of the architecture of how modern system on chips work. So I was able to engage and do some mailing list discussions before then. And then I had worked with people that, sort of in different roles in different companies as well. So I had some reputation. But actually my patch count in the mainline kernel was quite low. I'd spent a lot of time shipping Android devices, which is old, nasty, out of tree sort of stuff. So I would say that you can try to do this. Oh yeah, it's okay. I mean, it's just some guy clapping. So, you can definitely engage in this activity without having like a stellar reputation in the community. The point that I would say about that is, before you spend 6 months of your life trying to write like the most beautiful framework that instantly gets knacked, and I actually did that one time for a different piece of code. Put a really quick RFC, and it might even just be documentation. It might just be a documentation RFC where you just kind of describe what you think the interfaces should look like, and you describe what you're trying to do, and just see if there's a warm or cold reception to that before you waste time on something. So, if you're like a super senior guy and you already maintain some stuff, you can probably get away with just implementing it and putting it on the list and merging it pretty quickly. But yeah, if you're kind of starting from scratch within the community, get a mentor, publish early, publish often, and don't like waste too much time on something that you're not sure is going to get merged. So.
Thank you. Next question. Okay.
Thanks for the talk. First, I just wanted to ask how computers work, but that probably will be a long discussion.
Magic.
So, well, yeah. So, more practical question is: first, I'm from the user space. I have no business messing with the kernel, at least for now. But it's a common practice in user space to log everything and count everything. To collect as much data as you can to then later debug your code.
Right.
But then in the Linux kernel, it's probably very expensive, especially for the library. How this is missing from your talks, and I think it's very important to make a distinction where you should draw a line, what data you should collect in the library, and not in the device drivers. It should be clear for the device maintainer, and for the library, it very much depends on the use case.
Right.
So that's my question.
That's an excellent set of points. And so, yeah, there's a bunch of stuff that I should add to the slides. Like for instance, trace points. adopting trace points very early on when you're developing the subsystem. And actually, subsystems are the right place to put trace points more than the individual drivers, right? You want to see all those events happening in a common place. And so, yeah, that's one way to sort of help log the data a little bit. But actually, an interesting point about doing this type of logging of data in the kernel is that early on, when I first started writing the clock framework, we had some really old ways of doing things. Clocks are one of the first things you have to bring up on a platform. They're like a fundamental thing that you have to do when you deal with when booting. And so, for instance, my initial RFCs for the clock framework didn't use any memory allocation at all. If you only had static data tables, you could register with the framework. I mean, this is before the allocator came up. This is before the scheduler started to run. I mean, this was super early boot. And so I actually designed the framework around that. So yeah, there was basically no debugging, no logging, nothing like that where, I guess you could have, created like some kind of circular buffer and dumped stuff there. But no, it was very lean and mean. And over time, we actually, all the platforms that needed that static, sort of that static data mechanism, they all got updated, and now clocks are something that you can do during module init or late init. And now we have the luxury of being able to do more heavyweight kind of analytics and stuff like that. But I would say that, I think it's good to gather that data when you need it. I would say I don't spend a lot of time thinking about that stuff until there's a need for it, which is a difference, I think, from user space. And in fact, I would say, like, outside of the Linux kernel, sort of the state of like API design is somehow a lot better. I mean, if you look at, how many books and resources are there out there on like web API design and stuff like that, and I would say that's a more healthy discussion than what we have in Linux. I mean, in Linux, it's a bunch of like cowboys writing C code, right, and just reinventing it and doing it their own way every time. So I think those are very valid points. I don't have an answer for where that boundary is. I would say that's, for every subsystem, since we're a bunch of cowboys writing code, I mean, it's something that you decide yourself every time. So.
Okay, thank you.
Okay. We have about 2 minutes left. More questions? Вопросы? Да, на русском языке тоже приветствуются. Okay, so the favorite tip for me was about searching the makefiles lexicographically. It's a really nice thing.
The most important point.
Yeah,
for sure. Yeah.
Kidding. And thank you very much for your presentation.
Yeah, thank you all for attending.
Thank you.